In this 10th lecture, we look at analysis. A bit harder to define. One can see it as the process of breaking complex structures into smaller building blocks. Examples are Taylor series, decomposition of a function in calculus, or complex analysis, the Fourier decomposition in harmonic analysis, or the spectra in functional analysis, dimensional self-similarity in fractal objects. The area is quite technical. We therefore keep our lecture more in a tabloid style. We will just study some pop stars in the field. Examples are self-similar structures like the Menger sponge, the Hofstadter butterfly, the Mandelbrot set, or the new kid on the block, the Mandelbrot. Analysis has many parts. Each of them is actually a fully developed subject, usually taught in a single course. There are many applications, like in probability theory and stochastic processes, inverse problems, complex partial differential equations, or when looking at optimization processes in infinite dimensions. Here are some examples. We just flash some pictures. Picture of turbulence, fluid dynamics. You see here some particles which emulate a fluid, complex processes, also fluid dynamics. Here studied by backyard scientists. It's quite a popular subject on YouTube, these slow motion pictures, fantastic pictures. And inverse problems, analysis matters when solving inverse problems like in tomography. CAT scans allowed to look into the body.
Here, sophisticated computers to produce multiple images or pictures of the inside of the body. These cross-sectional images of the area being studied can then be examined on a computer monitor or printed.
The mathematics involves Fourier analysis, Taylor series, and linear algebra. Lots of interesting math is involved. Also, harmonic analysis is important when compressing digital data like pictures or sound or movies. It allows us to look into the small, where spectral properties, quantum mechanical properties are important. We can understand landscapes like mountains, city structures, flowers, leaves, transport in plants, fluid motion, cloud structures, star clusters, smoke, craters, galaxies, sea alkins, cauliflowers, ferns, trees, electrodes, art, strange attractors. We come to this in a lecture later on, like also chaos. Extrema problems are often fractal nature, like here the problem of the Kakaya problem of turning a needle, and spectra, this is the Hofstadter butterfly. Or in random matrix theory, here are random matrices which are which have some correlation. They often have spectra have fractal structure. This is the end of the first part. In this second part, we want to understand the definition of dimension. The concept has been generalized from integers to non-integer numbers. Familiar are spaces with integer dimension. A discrete set has dimension 0, a curve like a circle or a line has dimension 1, and a surface like a plane or a sphere has dimension 2. There is a nice formula which captures most objects nicely. I call it the Spock formula. Mathematicians call it the box counting dimension. The idea is to take a very small r and count the number of boxes of size r which are needed to cover the object. A formula gives then the dimension. Here is the movie in which this formula appears. It is Star Trek from 2005. Let's look at the line or a curve. Take a very small r. Now, how many boxes of length r do we need to cover it? It's roughly the length of the curve divided by r, give or take. So now if you look at the dimension formula and use the rules for log, we get d is equal to 1. Constant log c over log r goes to 0 for r going to 0. We see that here, again, in 2 dimensions, an object of dimension 2, we need about the area over r square boxes of side length r to cover it. Again, using the laws of log, we get that the dimension is close to 2 if r is close to 0. And again, this log of c over log of r, that goes to 0 if r goes to 0. Here's the first example of a fractal object. We need about 2 to the k, we need exactly 2 to the k boxes of length 1 over 3 to the k in order to cover the fractal. So with k equal to 1, we need 2 boxes, k equal to 2, we need 4, k equal to 3, we need 8, etc., etc. Here's the computation of the dimension. We see that the k falls away, and using also that the log of 3 to the minus k is log of 3 to the k, so we end up with log 2 over log 3. We don't even have to bother with the constant c in this case. The Cantor set is named after Georg Cantor, even though Henry Smith found it a bit earlier. Here's a statue of Smith. The definition of a fractal object is that it is a set of which the dimension is not an integer. We covered the Koch snowflake in detail on the whiteboard. It has been found by Helge van Koch. So it starts like with a triangle, and then you attach triangles, 3 triangles, triangle to each side, and then you do again the same construction again and again. And so each time when you divide it by 3, you add 4 more triangles, so the dimension is log 4 over log 3. Here's the Sierpinski carpet. It's a 2-dimensional analog of the Cantor set. You need 8 boxes of side length 1/3, 8 square boxes of side length 1/9, 8 to the k boxes of side length 1 over 3 to the k, and the dimension with that formula is log 8 over log 3. It's the Menger sponge. It's dealt with similarly. It's a 3-dimension. We need 20 boxes of side length 1/3, and the dimension is log 20 over log 3, which is a number between 2 and 3. Here's Carl Menger. The Sierpinski triangle needs n equal to 3 to the k boxes of side length 1 over 2 to the k. We can see that, for example, for k equal to 1, we need 3 boxes of side length 1/2. We need 9 boxes of side length 1/4, etc. The dimension is log 3 over log 2, which is bigger than 1 but smaller than 2. The Sierpinski pyramid, the 3-dimensional version of that, is technically no more a fractal, as its dimension is log 4 over log 2, which is 2. Here's an object from which we don't know the dimension. It's the tree of Pythagoras. Here's an animation. You can change the shape of a triangle and get each time a beautiful tree. The fractal is actually the boundary of that object. It appears to be a fractal. As far as I know, one has not computed the dimension yet. It probably depends on the triangle shape. You see, here's a isosceles triangle, and then the angle becomes again smaller. We go back to very small angle. Very beautiful fractal object, organic nature. Here's some literature about fractals, hundreds of books with in the subject, and this is the end of part B. In this last part, we want to understand the definition of the Mandelbrot set. It has a rich history and leads also to related objects for which the mathematics is still unexplored. You might have seen the object. It's a beautiful icon of complex dynamics. It was popularized by Benoit Mandelbrot, who lived close by after retiring near the Cambridge Mall. Mandelbrot here has one of his last appearances in a
There are some
TED
shapes
talk.
which have this peculiar property that each part is like the whole, but smaller.
He wrote in 1975 a very influential book, The Fractal Geometry of Nature. It has been popularized in many other books and films. We see a clip from this movie.
1958. The giant American corporation was pioneering a technology that would soon revolutionize the way we all live. The computer.
What is the length of a coastline? That was a question which Mandelbrot pondered. It depends on the scale. It is a fractal. He wrote in 1967 a science article about it. And one can ask this question also for other coasts, like the coastline of Massachusetts. I measured that once. You just count boxes, as we have seen in the last part of the lecture, and then compute the dimension, which is a slope. Just we take this Spock formula, and we get about 1.295. But let's go to complex dynamics. It started with Arthur Cayley, who was looking at the Newton method in the complex plane. So if you take a polynomial like z to the 4 minus 1, it has 4 roots. And if we start with a point z and apply the Newton method, we end up at one of the 4 roots. So there are 4 regions depending on which point we end with. And these regions are entangled in a very complicated way. And this is already an example of a complex dynamics. Mandelbrot looked at z squared plus c, where c is a parameter, and the Mandelbrot set is the parameter c, such the orbit of 0 stays bounded. We will come back to this definition later on. The set actually has been found first by Brooks and Matelsky in 1978, and Hubbard and Mandelbrot around 1980 rediscovered it. So this is the article of Brooks and Matelsky from 1978, where the first picture of the Mandelbrot set appears. Here's a nice poster I have in my office. It's just a photo which explains many parts of this set. Here are some pictures. You find them everywhere. Very beautiful. Peitgen and Richter have done that very early on in the 70s. Already made beautiful pictures. You can also make it 3D printable or place it in Google Earth and fly around. So here's another clip about Mandelbrot.
Did something Julia could never do. Use a computer to run the equations millions of times. He then turned the numbers from his Julia sets into points on a graph.
Here is a nice Mandelbrot zoom, probably the best one you can find on YouTube. It's 15 minutes long, so I cut it to 1 minute and then just take the 10 seconds. It goes to scale 10 to the minus 20. Let's try to understand better how the Mandelbrot set is defined. First of all, we need to recall about complex numbers, on which Gauss wrote, the true metaphysics of the square root of -1 is elusive. So there's a nice formula, which is the most beautiful formula in math. 1 plus e to the I pi is 0, which involves 0, 1, e, I, and pi. Benjamin Pierce once explained and said, it is absolutely paradoxical. We cannot understand it. We don't know what it means, but we have proved it, and therefore we know it is the truth. But the formula has been found by Euler. We don't need this formula. We just need addition of complex numbers and multiplication of complex numbers. The only thing you really need is that you know that I square is -1. And now to the definition of the Mandelbrot set. So we look at the map. Z goes to z squared plus c. C is a parameter. And M is the set of all C's such that the sequence orbit 0, t of 0, t of 0, etc. stays bounded. So here's some example. If you take C is equal to 0, then we stay at 0 all the time. So this is in the Mandelbrot set. C is equal to 1. We jump from 0 to 1, forth and back. Also this stays bounded, so we are in the Mandelbrot set. If we take C is equal to 2, then we have a 0, 2, 6, 38,456, and so on. This explodes, and we are no more in M. Also, for example, the point 1 plus I is not in N. So in order to find the Mandelbrot set, you have to do that for lots and lots of parameters C and see what happens. Here's a Mathematica code which explains this. And so we can then make a density plot. How many iterations do we need until we get outside the disk of radius 2? We will just see that the Mandelbrot set is inside the disk of radius 2 here. Here is that little result. You can check that if you are outside the disk of radius 2, then if you iterate it, you are getting further away. So this Mandelbrot set is contained in a bounded set, and this allows the computer to decide pretty quickly whether you are outside. Doherty and Hubbard, here we see pictures of them. They made the first mathematical breakthrough and also kind of named it the Mandelbrot set. It's funny that Mandelbrot first conjectured that the set is not connected, as the computer printout had some isolated specks of islands, and the editors of the paper erased those, somehow unwillingly corrected the first impression that the Mandelbrot set is not connected. But it's a mathematical theorem that the set is actually connected. Doherty is memorized also in the Doherty rabbit, which is a Julia set. So here's a three-dimensional analog of the Mandelbrot set. It's called the Mandel bulb. It has first been looked at by Daniel White in 2007. Paul Nylander looked at higher order versions. These are the versions which you see now mostly on YouTube. White was inspired also by the work of Rudy Rucker, who looked at similar constructs earlier on. So the Mandelbrot is now a YouTube star. So here is a short clip from a movie. You'll find another clip. People have made beautiful pictures. One of the most beautiful, so it's kind of intriguing how that looks. And there's almost nothing known mathematically that it's beautiful, the structures. Here's probably the most beautiful rendering. Despite its beauty, nobody has any mathematical results about the Mandelbrot. Is it connected or not? Nobody knows. This is the end of this third part and the end of the lecture.